Have you ever thought about materials that just don't seem to play by the rules? You know, they're not really a solid, but they're not exactly a liquid either. Well, today, we're diving into the super strange and fascinating world of these in-between materials. Right, so think about something like silly putty. If you pull it really fast, it snaps, just like a solid. But if you just leave it on a table for a while, it slowly spreads out into a puddle, like a thick liquid. So what's the deal? Is it a solid? Is it a liquid? Or is it somehow, crazily, both at the same time? Well, the answer to that little puzzle has a name: viscoelasticity. It's the official term for materials that show both viscous, or fluid-like behavior, and elastic, or solid-like behavior, whenever you stretch them, squish them, or twist them. It's this dual personality that makes them so incredibly unique. Let's really break down those two personalities. On one side, you have the elastic, solid-like part. The best way to think about this is a spring. You stretch it, it stores up that energy, and the second you let go, it snaps right back. That change is totally reversible. Then you've got the other side, the viscous, fluid-like part. Think about honey. It just flows, right? It loses energy as heat, and it's definitely not snapping back. That change is permanent. Viscoelastic materials, amazingly, manage to do both of these things. Okay, it's one thing to talk about springs and honey, but how do scientists and engineers actually predict what these materials are going to do? It turns out they use some surprisingly simple ideas to get a picture of what's happening on the inside. To model this whole thing, scientists basically use two building blocks. First, you've got the spring. That represents that snappy, elastic, instantaneous bounce back. And then there's something called a dashpot. The easiest way to picture a dashpot is to imagine a piston moving through a tube of thick oil. It resists the motion and perfectly represents that slow, gooey, viscous flow over time. Now, here's where it gets really clever. It all depends on how you arrange these parts. If you combine them, you get these incredibly powerful models. Stick a spring and a dashpot in a line, one after the other, and you've got the Maxwell model. That one's fantastic for predicting something we call stress relaxation. Put them side by side and parallel, and you get the Kelvin-Voigt model, which is perfect for predicting something else called creep. So let's talk about those two behaviors, creep and stress relaxation. These are not just abstract ideas from a model. They are real, measurable things that are basically the dead giveaways that you're dealing with a viscoelastic material. First up, let's talk about creep. Imagine you hang a heavy weight from a plastic beam. It's going to stretch a tiny bit right away. That's the elastic part talking. But if you just leave that weight hanging there for a few days or even months, you'd come back and notice the beam has slowly gotten longer. That super slow, time-dependent stretch under a constant load, that is creep. And the other side of that coin is stress relaxation. So this time, imagine stretching a rubber band between two nails and just leaving it there. It's held at a fixed length, a constant strain. At first, it's pulling back really hard, right? There's a lot of stress. But if you check it a day later, the internal structure of the rubber has kind of rearranged itself. The pulling force is decreased or relaxed, even though the stretch hasn't changed one bit. All right, so we've got the theory, we've got the models, we've got these weird phenomena, but where does any of this actually matter in the real world? Well, the applications are all over the place, but I want to show you one that might actually change the way you look at dinner. Yup, you heard that right. This fundamental concept from material science has a direct and pretty impactful application in the world of food. Specifically, we're talking about making tough chicken tender. And this isn't just some wild idea. Researchers writing in the journal Foods back in 2021 said flat out that these viscoelastic properties, creep and stress relaxation, could be the key to understanding and even predicting the texture of meat. So, naturally, they decided to test it. They decided to tackle a real problem in the poultry industry, a condition called wooden breast. It makes chicken meat really hard and tough, not pleasant at all. Their big idea was to blast this tough meat with high-power ultrasound to see if they could physically change its viscoelastic properties. And the result? It was absolutely dramatic. After they hit it with the ultrasound, the shear force, which is really just a scientific way to measure how much effort it takes to cut the meat, dropped by a whopping 27%. This chart just says it all. You can see it right here. Before the treatment, the hardness was way up there, over 3,600 grams of force. After the ultrasound, it plummeted down to just over 2,600. I mean, by literally shaking up the material's internal structure, they made it so much more tender. This is just such a perfect example, isn't it? It shows that viscoelasticity isn't just some dusty concept in a textbook. If you understand how that viscous part and that elastic part play together, you can use energy, like sound waves, to physically change a material for the better. It's incredible. And once you start looking for it, you realize this principle is everywhere. It's in the shock absorbers in your car that eat up the bumps in the road. It's in your memory foam mattress that perfectly molds to your body. It's in the seals and gaskets that have to hold their shape for years. It's even fundamental to how we manufacture plastics. It's everywhere. So here's the big takeaway. Being neither a perfect solid nor a perfect liquid isn't some kind of defect. This in-between nature of viscoelasticity is actually a feature. It's a property that lets materials absorb energy, relieve stress, and adapt over time. And it's something that brilliant engineers and scientists are using to literally design the world around us. Which really leaves us with a pretty cool question to think about, right? We've gone from the simple idea of springs and gooey dashpots all the way to making chicken more delicious. So if we can solve that problem by mastering this in-between state, what's next? Better earthquake-proof buildings? More comfortable shoes? The possibilities are just absolutely amazing. Thanks so much for joining me.